Yeah, so we had the machine learning summer school in Karloa, a couple of cottages and kangaroos between the cottages. So then it moved to Canberra, and now we are here in Sydney. And it's great to see that there are so many people now interested in machine learning. The slides I will show you today are already online, an early version of it, but I would like to warn you, something strange has happened when I sent them on Saturday to Edwin. I sent a 5 megabyte file, and it turned out to be a 100 megabyte file. So I didn't know that the internet is also taking the population count in the number of people in the city into account, because I'm coming from Canberra, and Sydney is quite bigger, so maybe that's a factor. So we will put a new version online, because it's only 5 megabyte. I don't know what happened. Don't try to download all at the same time now, 100 megabyte. Okay, the slides, you will probably see the number here, 211. Don't be scared. The slides have contents, and they are clickable. And we will not rush through them. But what I want to give you is, I want to give you an overview of machine learning topics. And so for the people who already know everything, I hope it's a good refresher. For the other people, I hope we can get you to the level that you can then start to follow the other lectures. So when we talk about machine learning, there are many, many different meanings to learning, and I've just put a few of them here. So learning about machine learning is acquiring knowledge. That's normally not what we understand when we talk about machine learning. Acquiring skills, that's already something we talk about machine learning, learning to drive a car. Finding patterns, that's learning to read an X-ray image. Or discovering causal relationships, and that is a much hotter topic now, finding causal relations, because that is what we are really looking for when we do science. We are looking for causal relationships, and the question is, how much can machine learning help us to automate part of doing science, collecting a lot of data, deciding which experiments to do. So to be a little bit more formal, machine learning is concerned with the design and development of algorithms that allow computers, machines, to improve their performance over time based on data. So here we have a little bit more of a way to decide if something is machine learning and how to do it. Because what we are doing, we are learning from past experience. We want to generalize on and apply what we have learned to new data. And in order to do that, we need to think about how can we really quantify learning? How can we quantify that we are improving our performance? So whenever you want to solve a machine learning problem, I think the first thing to think about is really, are you able to somehow quantify the performance you want to measure? That is a hard question. If you have that, then you can try out a lot of things. And you can make it a little bit more formal, and that is from Tom Mitchell. A computer program is said to learn from experience E with respect to some class of task T, and performance measure P. If its performance at task T as measured by P improves with experience E. So that's very formal, but still, sit back if you want to do machine learning and try to identify what are the ingredients, what are the tasks, what are the measures, and what is experience. Can you really write it down? So just a few examples. Everybody knows junk mail, and computers are now able to deal with it. So the computer learns from you saying, well, this is junk mail for me, and that is not junk mail. And then over time, it adapts to what you think is junk or no junk. And it does it all the time online. It doesn't stop. It all the time learns. Because the people who create the junk mail, they are also clever. They learn from what the junk mail filters have learned, and so they change what they produce as junk. A classical example, handwritten digit recognition. That was a hot topic 25 years ago, because if you want to automate the post office, that was a time when people still used letters. So if you want to automate the post office, you need to be able to recognize handwritten digits. Backgammon, famous example, a computer program which learned by playing against itself and plays now on the world level, on the level of a human world champion. This is another example what machine learning can do. You take an image, that is the original, you add noise to it, and you throw the original away. And now the question is, can you denoise this image? So what this student here did, he used natural images, photos from natural scenes, not including this. And he just looked at a number of pixels, let's say 3 by 3 or 5 by 5, and created a statistics over these patches. Because each of these patch appears with a higher or lower probability. Totally random pixels will probably be not seen so often. But if you have natural scenes, you might have a lot of water and a lot of sky, so you might have larger patches of blue, or if it's with grass, then you have patches of green. So he only used that statistics and never had seen this original image and could then denoise it into this image here. And if you compare this and this, it looks quite good. This is another example, although some people might argue that is really just signal processing. So you have a number of microphones and you have a number of people talking at the same time. And you can, just by applying probability theory and some MATLAB program, which is only a few lines, you can then take all these mixed signals and filter out each of the single speakers. This is another example where I've worked with some people here in Sydney. The problem with mobile networks is that you can't really get a good connection for videos. So it would be a nice idea if you could predict what a user wants to watch in the future, and then when he or she is at home or at university, you can already download all of that, because memory is cheap on our mobile phones. And then you can watch it while you have a bad connectivity or when you are out in the bush. But in order to do that, you need to predict what the user really wants to watch in the future. How can you learn that? So we created this application here, and people who wanted to download it had to allow us to monitor what they chose, in which order they chose the videos, and where they clicked. So we had about 500,000 downloads, 50,000 downloads sustainable, so people used it over a number of weeks. And then we basically got heaps of data from each of these devices. Now we try to figure out what the user wanted to watch next. Machine learning question. This is another project which is still ongoing in Canberra. If you want to have more solar panels on the roofs, and more solar energy is coming from solar panels on residential roofs, then you have a problem if a cloud comes, because suddenly the energy drops massively. Currently, we don't have so much solar energy from solar power, so that is not a big problem. It's still in the noise which you have anyway, because people switch on their washing machine and switch it off. So what we do is we distribute sensors over Canberra, and then we hope that with using these sensors, which measure the current output from some of the solar cells, plus images which we take from the skies, which tell us something about how the clouds move, and then applying clever machine learning, we want to predict what is the output of a whole suburb or a sub-suburb, the output of the energy in the next 5 to 60 minutes. So again, we get a lot of data, but there are a lot of machine learning problems involved here. There are trees which shadow these solar panels, and then we have to learn that for each single place where we are monitoring. Then we have to aggregate that into an aggregation of how much solar energy is coming. Okay, other applications of machine learning: autonomous robotics, obvious, detecting credit card fraud, detecting network intrusions. In bioinformatics, we have massive amounts of data, lots of snippets from DNA, for instance, and we want to figure out what is the real DNA, or how similar are samples taken from different DNA, only by looking at all these snippets and doing statistics and machine learning over it. Neuroscience, medical diagnosis, stock market analysis, and it goes on. So why do we machine learning in all these examples and in all the other examples? Well, there are a couple of things where you really need machine learning. So one is when we humans can't really explain how it is done. So for instance, speech, we are not really able to explain how we speak. And machine learning helps here to solve the problem of speech recognition. If humans are not around for help on Mars, underwater robotics, we need a system which is adaptive, which learns from the environment. If we have huge amounts of data with possible hidden relationships and correlations, again, computers and machine learning can also help us here. If the environment changes fast, so all your mobile phones have an adaptive algorithm which checks every time in which of the many channels signals are distributed, which of the channels are the best. And then, of course, if you have something which you need to adapt to many particular cases like junk mail, you create a program which then learns from each individual user. Okay, why is there so growing interest in machine learning, as we, for instance, see here? There are a couple of reasons. We have huge amount of data available now. I still remember 15 years ago buying some accelerometer. It had this size, and it cost about $10,000. With the airbags in the cars, now you have these micro-mechanical sensors which you have in your mobile phone, which measures acceleration, and it costs you a few bucks. So all these devices create data. So we have a huge amount of data available now compared to times earlier. There are, of course, advances in machine learning, in theory and optimization. We have an increased computing power, speeds, cores, storage size, and we also have an increased availability of computing power. So all this contributes to the fact that what do we do with all this massive amount of data which is created faster and faster. So I just want to throw in a slide here, which is, I didn't find the right place, so I just chose to do it here when we are talking about computers. We will not talk about this aspect of machine learning in this introduction, but we are running all of this on machines. And when you want to do machine learning, you should have an idea what the speed of your computer is. And this just gives you an idea that there are magnitudes of differences in speed with which things occur on your computer. So you have the L1 cache with a half a nanoseconds, and even just unlocking and locking a mutex, so you have two threads running, you want to synchronize them, that takes 200 times longer. And though you go up to compressing 1 kilobyte to 10 microseconds, and you go up to sending a packet, and we are still here on 150 milliseconds. So just to make you aware, there's a huge scale, and when you really want to make efficient machine learning algorithms, you have to know something about this scale of speed. So I just want to point you to this. As I said, we will not go deeper here, but just try to contemplate about this. How many scales do we have here? Well, 10 to the 6, 10 to the 8. Huge difference. Okay, coming back to the main line, there are a lot of related fields. I won't go into detail here. Just mention that game theory and machine learning, as in the last years, have had quite interesting connections. Okay, so a few words which you probably have heard. We have different types of learning. So we have unsupervised learning, where we don't assume that we have labeled data. So we take data, we try to associate them, we try to cluster them, we try to estimate the density. Then we have supervised learning, where the classical examples are regression and classification. We have a whole area of reinforcement learning, and I'll say something about that later. And then we have other areas which are partially related, partially have their specific touch. So active learning, where the learning system, for instance, chooses what data to explore next. So simplest example is unsupervised learning. You're given a bunch of data, and you're trying to find some structure. So you could say, for instance, okay, which points cluster? But that is not the only question you can ask. You can ask many other questions over this data. For instance, which data points form almost a square? So you can put a lot of structures onto this data set and try to figure out where you find these structures. Then we have supervised learning. Here we are given data plus labels. So here in this case, I just have red and blue labels. And then we ask the question, for the future, we are given a new data point. Now, what is the label for this data point? Is it red or is it blue? Reinforcement learning, we'll not go deeper into that here. The basic idea is you have an agent. The agent observes something, and then he chooses an action. And depending on the action, then there is a reward from the environment. The action gets this reward, and then it goes to the next step again, observes, chooses an action, and gets a reward. So that is a typical setup. For instance, if you play a game, if you play chess, the reward doesn't always have to be instantaneous. So the problem here is if you only get the rewards 20 steps later, what do you make of the information here that you have chosen an action? And there is a natural dichotomy here. You can try to explore things which you haven't seen yet, or you can try to exploit things which you already know. So if you already know that doing this action will give you a good reward, you can say, well, I'm doing that again, and you will get the reward. But you can also say, well, there are things which I haven't tried out, so maybe I should try them, and then there is a chance that I don't get a reward, but at least I've learned something. So basically, we are all doing this. When you go to study, you say, well, I don't earn money now, but I want to learn something. I explore something. You could also say, well, I don't want to learn. I just want to use my skills, which I have, and get a salary from that. So this is reinforcement learning, and it has a natural focus on online performance, as you can see. Okay, so let's get a little bit more formal, and I will just show all of this at you on two slides, because we don't really have to go time to go into all the details here, but I want you to know that these are basic concepts. So when we do probability theory, we have a sample space, and I take here the example of a fair six-sided die. So we have 1, 2, 3, 4, 5, 6 eyes as 6 possible outcomes. And then we have events. So we can, for instance, look for the event that the eyes are even or the eyes are odd. And these are subsets of this sample space. And then we can ask for the probability of these events. So if the probability of a 3 is, for instance, 1/6, the probability of the event odd is half. It's the same as the probability of the event even. If you work with continuous sample spaces, there is some subtlety here because not all sets are measurable. I don't want to go into details. If you want to know more about that measure theory, then look into sigma algebras, because in continuous spaces, not all sets are measurable. So you have to choose only the subsets which are measurable. The other subsets don't count. And then we have the concept of an outcome, so that we do an experiment, so we see some outcome here. And we have a concept of a conditional probability. So for instance, if we already know that the number of eyes is odd, what is then the probability that we find a 3? And that means we have to take into account that we are no longer looking at all possible outcomes, but only on a subset. And that's called conditional probability. I would suggest you not to use the formulation, given odd, what is the outcome of 3? Because that is often misleading. Generally speaking, the conditional probability is still a function of 2 variables. What you plug in here and what you plug in here. So a better way to think about this is conditioned on that we only look at the odd eyes. What is the probability of getting a 3? Okay, and then we have some general axioms for probability theory. The empty set has probability 0, the whole set has probability 1, and everything in between is here. Then we have the rules that the intersection and the union and the intersection are exactly the sum of these probabilities. And here is the probability of A conditioned on B, multiplied with the probability of B is exactly the probability of the intersection of A and B. And if you put this all together, you end up with 2 rules for probability theory. And that's basically all you ever need to know about probability theory. It is the sum rule that if you have a random variable x and you think you have a probability which also depends on some other variable y, but you sum over all possible values for y, then you end up with a probability for x alone. So we can use that in both ways. We can say, well, let's introduce another variable y, and then let's just sum over all of that. Or we can go in this direction and say, well, we are not really interested in the probability of y. Then let's sum over all of it, and we end up with the probability of x alone. And then we have the product rule, which involves, again, the conditional probability. So the joint probability is a product of the conditional probability times the probability of y. So there's a little bit more of jargon here, and I use the unfair coin as an example here to explain what this means. So we are using T for tail and head for head, H for head, and we can talk about the likelihood. Now our assumption here is that that might not be a fair coin. So the probability of head is some value theta, and theta can be between 0 and 1. If it were a fair coin, theta would be 0.5, but we make it more flexible here. So then we can ask the question, what is the likelihood of seeing head, head, tail, head, given that I know theta? Well, assuming that the throwing of the coin is independent each time I do it, then we can just multiply the probabilities, and the probabilities are theta, theta, tail is 1 minus theta, because that's the other outcome, and times theta. And then we can ask, okay, if I've seen head, head, tail, head, and I don't know theta, what is the maximum likelihood of seeing this outcome, given that I assume it depends on theta? And if you do the math here, it will be 3/4. So this is a biased coin. Of course, I mean, you probably already know that doing this small experiment will not give you a very good idea about what theta really is for that coin. But if you do it for a long stretch of coin throwing, then you might get a better approximation. So then we can also assume that we have some distribution over this theta. And if we don't know anything about that, we just assume it's constant over some range. Then we have evidence. That's the probability of this outcome here. And we also can calculate the posterior. And we'll talk about Bayes' rule soon. That is the likelihood multiplied with the prior and then normalized. So that's the posterior. And we can also ask the question, what is the setting for theta, which gives us the maximum posterior? Another interesting question we can ask, okay, now we have seen head, head, tail, head. What is the probability that we can see H as a head as the next one? And that is the predictive distribution. So we have seen some data. Now we want to know what's the probability of seeing the next data. And then we have concepts of expectations. So here we take into account the probability of probability distribution over theta. And for instance, we can calculate the expectation of some function. Or we can calculate the variance of, for instance, theta here, by asking what is the expectation of the squared deviation from the expectation. And all these concepts work also for probability densities, where we no longer have discrete events like here, but we have a continuum which basically boils down to doing a limit with epsilon going to 0. Okay, now let's start with real machine learning. So here we have a very simple example. We produce some data from some given function, but then we throw away the function, because in reality, all we have is just a bunch of data. And here's a little bit of notation. These are vectors, and the targets. These are the y values here, if you want, in this graph. This is also a vector. And each of these elements are coming from the real numbers. And now we have to decide, first of all, what model to use. And here we take a polynomial, so we just take powers of x and multiply them with some number. So note that this is a nonlinear function of the axis here, but it's a linear function of the model parameters w. And so for each of the polynomial powers, also for each of these m which we choose, we can ask what are the best parameters w to fit these points here. Well, to fit, we need to really define what to fit means. And so we need a performance measure. And here in our case, we'll take the squared distance just for simplicity, the squared distance from our function, we will take that as performance measure. And now we are able to measure whether a curve which we find, a polynomial which we find, is closer or not too close to our data. So the simplest example is R. Let's take a zero-order polynomial. So our function will be this red function, which doesn't approximate our blue points very nicely. We can go to a linear function, which gets a little bit better, but not really much better. We can go to third-order polynomial, and we already get a bit of it. And now we can go to a ninth-order polynomial, and we have a perfect fit of our data. So we have learned everything what we want to know about our data. Unfortunately, not quite so, because you see that if our data are really coming from some underlying function, which is a sign, then we will do a very bad job at all the points where we are not hitting our training data. So that's called overfitting. And how can we figure out that this happens? Well, we take not only our training data, but we get 100 new points, and we do the same experiment. So what you see here is, with our training data, if we got a higher order polynomial, we could make the error to 0. But if we do this with our test data, then this will blow up. Why will it blow up? Well, because here we will do a very bad prediction for data points which are in between what we have seen. So if you look at the parameters, you also see that the parameters, the W's, start to really grow to very huge positive and negative numbers. And that is a sign that we are really overfitting here. So what can we do? Well, we can try to get more data. And then a ninth order polynomial for 15 data points is already a little bit better. We can get even more data. Let's say we have 100 data points, and then you see that we are doing already quite good, although we did assume a ninth order polynomial. So just the heuristics is you need at least 5 to 10 times as many data points than you have parameters. But this is with a grain of salt, because the number of parameters is not necessarily a measurement of the complexity of your model. So we'll later see this with the Bayesian approach. So we saw that problem was that our W's were increasing in magnitude to a huge number. So one way would be to say, well, let's try to keep our W's small. So let's try to keep the weights small. And that's called regularization. So here we have the error term, which we want to make small, but we add something to this error term, which is the magnitude of the squared magnitude of the weights. So this is just the squared norm of our weight vector here. And now we have two goals at the same time. One is we want to make the error small, but at the same time we want to make the W small. So you already remember, if this lambda is 0, then this is our original problem. And we are not doing a good job because we are overfitting. Now, if we make this lambda very big, then this error function tries to make the W as small as it can, and it will be very, very close to 0. That's the other extreme, which is also not so good. So we want something in the middle. So here's an example. If we have the logarithm here of our lambda minus 18, we are doing quite good job. if we make it much, much bigger, then it goes close to a linear function, because now we are over-regularizing. We are really just trying to make the w's as small as possible. And so we're getting something which is close to 0. Again, you can test the approach. And using some test set, you can see now that the training error and the test error behave in this way here if you plot it versus the regularization parameter. So if the regularization is becoming bigger and bigger, you're making bigger errors. But if you want to choose your lambda, then you should choose a lambda in the area where the test error is the smallest, and you still get a good regularization. So you would choose something like this here. So that is a very important thing in machine learning, and I would like to repeat it 10 times. We are not interested in reproducing our training data as best as we can. We are interested in generalizing well so that what we have learned can be applied to unseen data. It's really worth thinking about it and repeating it, because I meet people again and again who tell me, oh, look, I'm reproducing my training data so perfectly. And I say, well, that's not machine learning. So the real point is we want to generalize well. And well, one way is if you have a lot of data, you just chop part of this data off and use it for testing. And then you can verify that what you have learned works also with new data. Now, sometimes you don't have a lot of data. And Edwin can tell something about that. He has worked on a geothermal project where they use data from drilling holes into the ground of Australia, where each of these holes costs a few millions. So you don't have abundant data available. But then the question is, what do you do with the existing data? And the idea is that, well, we need to partition into a training and validation set. But the idea is that we partition our data into a number of parts, and we train on S-1 parts, and then we test on the remaining part. But we do this a couple of times by choosing the test part in different segments here. So each of the segments will once be a test part, and all the other times it will be part of the training part. And then we take the error of all of these predictions for the unseen data here, and we take the mean of the error. So that's called S-fold cross-validation, and it's a good way of making the best use if you have a limited number of data. Okay, so we already went through part of the linear regression, because that's what we really did when we tried to fit a curve to our data points. Here I just want to stress that the word model is used in different ways in machine learning. So you have a model, and it depends on parameters W. So for instance, here I've just drawn 3 models which I get for plugging different W's into my linear regression. So for each of the W, I get a different model. And what we are looking for is the best model. Means we are looking for the model for which the parameter settings give us some smallest error or some other performance measure. So we, in fact, have, when we choose a model, we have a whole set of different models depending on what we plug in as a W. And then we are looking for the W which gives us the best model which is closest to the data. So that's what we already did. So we can generalize this a little bit by also taking into account that we don't need to work directly on our initial data. We can take some functions over the initial data. And so we have a little bit more general model. It's still linear in the W's, but now we have these basis functions or these features, which we can call them, over our input data. And we will see in a moment that finding the right features is often already 50% of your machine learning problem. If you have the right features, then you can apply very simple methods. If you have bad features, well, you have to look for very complicated methods. So I just want to generalize this a little bit here by introducing these features. But nothing really has changed. It's just that we have some transformation of the inputs. So for instance, here you can have polynomial basis functions where you just take the power of x, if you're in a scalar case, as features. They are, in fact, not so good. Polynomial functions are not good. And there is one reason which you can easily understand. Because a polynomial, if you change something, it changes everywhere. Now, in machine learning, that is not such a good idea. If you want to somehow improve here, because some of the data points are not so well represented, then you don't want to change everything you have already found here. So polynomials, because they are global functions, are not so good. But they are easy to explain. That's why I started with them. So we can, for instance, take a Gaussian basis functions. So each of the function only represents some limited area. And then we combine them by multiplying with our parameters, W. Or we can take sigmoid functions, or you can go to multidimensional representations. So you take wavelets as your basis functions. And then you're looking for the best combination of the wavelets. So wavelets are localized in space and frequency. So they sit, so to speak, between a Fourier transform where you only look at the frequencies and the representation in the spatial coordinates. They sit in between as a representation which has both space and frequency components. And you can go to splines. So you can make these features whatever you want and still work with a linear model. Okay, up to here we have really not talked about machine learning and probability. So in the next slides I will show you, even in our simple example where we took the squared error, there is a deep connection between probabilities. And if you think back, people have used squared errors for hundreds of years. You will see now that there is a relation to probability theory. So what we do is we assume that the target which we'll see comes from some deterministic function which depends on our inputs x and our w's, plus some noise. So we are making measurements, and the measurements are always noisy. There is always something which creates a little bit of non-deterministic contribution here. And for the noise, we will assume that it's zero mean, and it's a Gaussian random variable. And we use a precision of beta. So precision is just the inverse of the variance. Just some of the formulas are easier to write with the precision. Nothing special here. So what does it mean that we have added this noise here to our measurement process? Well, the probability of seeing some target is a function, of course, of our inputs, our weights, and this noise. And now we make this special assumption that the noise is zero mean Gaussian, means that the target and the deterministic parts are related by this normal distribution here with the precision beta, or the variance beta inverse. Now, where do I have the... I'm missing a slide, sorry. So that is for one measurement. But we are making a lot of measurements. And now we are making an additional assumption. We assume that all the measurements which we are doing have the same noise. So they are coming from the same Gaussian distribution. And that each of this measurement is independent of the other. So that's a crucial assumption here. It automatically rules out that we can deal with sequences of data where the sequence really matters. Here we're not assuming the sequence matters. The order in which you do the measurement doesn't matter. And this is called independent and identically distributed, and it's very often abbreviated IID. So you will see that very often, as an assumption, the data are IID. And it's good when you work with IID data to look at your data and, for instance, to randomize your data. Because the sequence does not matter. It should not matter. So I've seen, for instance, people who looked at some data that with 3 different classes, and for each of the class you had 50 data points, and then they used 75 data points for training, and they used 75 data points for testing. Now, if you do it in the order that first come 50 points from class 1, then come 25 points from class 2, you will never see class 3 in your data when you train. So here again, if it's IID, you should randomize your data, though you have each of the 3 classes in your 75 training data. So IID. Good. So this is a practical aspect that you can randomize, and you possibly should randomize your data to not depend on some special order of your data. But there is a theoretical consequence of that. Because of this, we can just multiply the probability for each of the single data points. So we can just multiply all these normal distributions which share the same variance here. So we have a product, and now we are trying to figure out what is the best setting for the W. Well, that's a little bit hard to deal with, so we need some trick here. And again, as in many cases, the logarithmic function will come to our help, because the logarithmic function is a monotonous function. So instead of talking about the product of something, we can take the logarithm, and then if we do that, we end up now with the sum of the logarithms of the normal distributions. And well, what does the logarithm do? It just takes products, makes them into terms which are added, and then so we get something here, the beta, we get some constant from the normal distribution, and we get another term which is the exponent of this product of normal distributions. Because we take the logarithm, the exponent becomes just a quadratic term here. And you can see that now, if we try to maximize the probability here, if we are trying to find the W and the beta which maximizes this probability, this corresponds to minimizing this term here, because we have a minus sign here. So here you see, this is a quadratic term. That's what we usually do. We try to minimize the quadratic error. But what it really is, or you can look at it this from another angle, is trying to maximize the probability of seeing the target data if you're given the input data and then if you're given W and beta here, which of course we want to find. Okay, this is just a little bit of linear algebra. We can rewrite this all in much more compact forms by introducing this phi function, which is all these features taken over the first data point, over the second data point, and so on. And if you have decided your features, you can write that down for your training data. And then you can calculate phi transpose phi, invert that, and multiply it with phi transpose. Apply it to your target, and that will give you the best W for this setting. So we can calculate in this case what the best W is. We can also go further, which I didn't do here, and that's already the first result which we couldn't deduce from the squared error alone. We can now ask the question, well, what is the beta the best beta which maximizes the probability of seeing these targets given this input data? So we can also find the maximum likelihood solution for the noise term. And then we can go further and say, well, now let's add some regularizer, because we know we should do regularization to not overfit. And if we assume we have an L2 regularizer, which is exactly this squared term of our components here, then the maximum likelihood solution changes slightly here by introducing the lambda with the identity here. Now, the good thing is here, and I didn't mention that, this could be, if you choose too many features or if you choose features which basically are the same, this could be a non-invertible matrix here, because it is singular if it has not full column rank. Here in this case, no problem, because we are always adding a positive number, the regularization constant with the identity, to this. So even if this is rank deficient, we can still invert the whole thing here. But we could also use a different regularizer, not the squared norm. We could, for instance, just say, well, let's just add up the components. Not the squared components, but the absolute value of the components. And that's called an L1 regularizer. And then we can still solve this, but we cannot solve it anymore in a closed form solution. We have to run a computer program now. Which brings me to this whole family of Q norms, which are defined in this way. There is some error here, I think. Sorry, there must be a square root, a root of Q over the sum. So what we usually use is the squared error here. And if you look at a contour, it will be a circle. So if this is one component, the other component, then if the square adds up to 1, that is this contour. If we go to the 1 norm, that will be the contour. And then we can even go further with the Q to go to these non-convex contours here. Now, why would you use the 1 norm, for instance? Well, it's already written here. If we use the 1 norm, we will get sparse solutions. And sparse means that some of our W's, if they are close to 0, they will be put to 0. So if we have a large vector of W's, many of these entries in our weight vector will go to 0. And there's a geometrical reason behind that. Think of the normal error as this function here. So if I go out from this, it will increase. And then think of our regularizer, which we add to the error function this here. So if we go out to this, it will increase. And then we are looking for a W for which the sum of these two is optimal. Now, because they are increasing with different rates, it will be somewhere here where the optimal W will be found. If we do that with the one norm, we have this contours here. And now again, if you go out from here, it will increase the one norm. And here, this is the same error function as before. But what happens here, because of this contour, with high probability, you will meet one of the corner points here. But what does it mean to meet the corner point here? Well, that means that this component will be 0. And now you can think of that not in 2 dimensions, think of that in 100 dimensions, and I hope everybody has a picture. So you will end up on some corners, and many of the components will be 0 because of this effect. So if you use the L1 norm, you automatically get a sparse solution. And that means you can compress your representation into a smaller set of variables because you only have some of the W's which really contribute to your solution. Okay. Now let's do something with Bayes' theorem, because we haven't touched that yet. So far we have done maximum likelihood solutions. So we only looked at the likelihood of the data. Yeah? You remember? This is the likelihood of the data. The probability of seeing the target if that is our prediction. So I just try to remind you, Bayes' theorem, we have a posterior, we have a likelihood, we have a prior, and we need to normalize that because we want the posterior to also be a probability distribution. And I already showed you this was the likelihood for our IID data. So we have this product here for the likelihood. And what that means is here the picture I was looking for before, that we have our target value for each of the data points, but there's a Gaussian distribution, there's some noise. So we might not get the deterministic output we are looking for, but we get something off in the y direction here. So if we want to do Bayes, we need to do this multiplication here and end up with a posterior. But we want to do it in a clever way, meaning that if we have some data, we start with some prior. Now we add some data, we get some posterior. And there is no reason why we should not be able to do this again and again. But if we want to do it mathematically, we need some nice property here that the prior and the posterior have to belong to the same family. Because the parameters we get here, we want to use them then as prior when we add another data point. So that brings us to the concept of a conjugate prior. If we are given some likelihood, and the likelihood is some family of, or some distribution, then we can find conjugate priors which have the property that if multiplied with that likelihood, give us the same type, the same family of probability distribution again. So here are a number of these conjugate priors for discrete distributions, and here for continuous distributions. And there is a very nice property that if the likelihood is normal distribution, then the conjugate prior is also normal. That means we can multiply 2 Gaussian, we still get a Gaussian distribution. And we will use that now in some experiment. So we start with no data, so we have a prior over our parameters. Then we get a data point, and we take the likelihood of this data point and apply Bayes' theorem, and then we get the posterior of that. Then we take this as a new prior for the second data point. Write down the likelihood for the second data point, apply Bayes, and then we get the posterior distribution. Now, to remind you, the posterior distribution tells us what is the probability of W, given that we have seen the targets and the inputs of our training data. So here in our case, we have already 2 data points, so we can look at the probability of this W. And I have created some data, and hopefully my experiment will run now. So I'm using some very nice software here. It's IPython notebook, very much recommended. It allows you to write, I'll show you the stuff. It allows you to write text together with explanations and code into one file. And then you can just evaluate that and store, so to speak, store your whole experiment in one file. If you use commercial software like Mathematica or MATLAB, you can do that too. But Python is for free. IPython is for free, so please try it. And let's go to our last cell here. And now but that's okay. So we have 2 W's here. We have a W0 and a W1, because we want only to find a linear function. And the linear function only has 2 parameters. The W0, the bias or the offset, and the gradient. And here I'm plotting the distribution over these W's before we get data points. And here I'm only assuming that, well, I don't know really very much about it, but I know that the W shouldn't be too far from 0. So I put a Gaussian distribution over the W's. Now I have this probability over the W's. I can already do an experiment. I can just say, OK, random generator, give me some samples from this distribution. And so I get W's, always pairs. And I can then use these pairs and plot a line. So I get one line here. That's an example which I've drawn from this distribution. And I draw another pair of W's. I get this line. And I get this line, and I get this line. But we haven't done any experiment yet. It's just the probability of W and making experiments with samples from this probability distribution. Now we add the first data point here. And for this data point, we can write down the likelihood, because we are assuming there is some noise. So we have this as the likelihood for this data point here. Why is it a straight line? Well, if you think about our curve should go close through this point. So what we can only vary is some line which is always close to this point. So that means that the bias and the gradient are linearly related. That is the reason why we get for the likelihood this distribution here. It's the distribution of the probability of the target if we have seen the X. And then we multiply. Now we apply Bayes. We multiply the prior with the likelihood. And so we get this as an output. So that's our first step. We take one data point, go from a prior, get a probability distribution over W, conditioned on, in our case, it's just one X and one T, because we only have seen one data point here. Now we go to the next step. We take this as our prior. And we take a second data point from our data set. Or before that, again, we can draw samples from our W distribution, and then we get this kind of lines. And if you compare it to this here, you see that because we had this evidence here, we saw this data point, we already get curves which are close to this data point, as it should be. Now we take a second data point, we write down the likelihood. It looks a little bit different because the data point is in a different position here. We multiply this and we multiply this together. And now I can do this, let's say, for 10 data points. So I leave the first one as it is. And I hope that my program does work. Ahead. Ah, yeah, it's coming here. No, that's not right. Here we are. Okay, so at step 10, we had a number of data points. So we already got a much, much more focused distribution over the W. And now we take another data point, which makes this a little bit smaller, but you can't really see these differences here. But with 10 data points, we basically went from this prior, which was just chosen arbitrarily, to this, and now we get this here, and we can continue this for more data points. This is interesting behavior. Okay. So let's go to 40 data points. And you see now that our distribution is already so focused that if we draw samples from it, we get things which are very close and very similar to each other. And you can see that here the next step makes it even smaller. And it will focus more and more. Now, just to finish this off, you would say, well, I cheated because I took the prior around 0. And of course, then you will find some solution there. So I'm now doing a different experiment. I take a prior which is, the probability is minus 1,000, so it's very, very far away. That's why I can't really plot it here. And I take one data point, it doesn't change that very much. But if I take a lot of data points, then I get the same result as I would have gotten after the same amount of data, or close to the same amount of data in the first example. So it doesn't really matter so much if I have enough data. It doesn't matter so much where your prior sits. There's only one condition, and we need to remember that. If your prior has probability 0 in the region where your solution should be found, then multiplying 0 with your likelihood will give you a posterior which is 0. So you will never find your solution. So you need only to make sure that there is a non-zero probability for your prior in the regions where you expect your solution. For the Gaussian, that is not a big problem because the Gaussian is non-zero everywhere, at least theoretically, not on your computer. But if you work with other distributions, you have to be careful with this. Okay. So that is, again, on the slides here. Okay, we have 5 minutes left to the break. And so let me just show you a little bit about the predictive distribution. I already mentioned it before, but I want to also just show you a little bit how we use the properties of probabilities together with knowledge about how we do machine learning to get interesting results. So we know what is the predictive distribution. It's again defined here. We have some training data, and I call them capital X. We have some training target, and this is the T. And then I learn something, and now I take a new data point, X, and I ask, what is the probability of seeing T? Again, we train on this data. Now, then we take a new data point, a test point, and we ask, what's the probability of T? Well, how can we calculate this probability? Well, first of all, we write it there. And then we think about what else is in our process. Well, we have this W, because our model has some weights. So we have the W's. But the W's don't appear here. Well, so let's just introduce W by applying the sum rule. And the sum rule says, well, just plug in a W and take an integral or a sum over all possible values for W. So that's good, because now we have a W in our formula here. Now, we can look at this and apply the product rule, which introduces a conditional probability T conditioned on W times the P of W. Just the product rule. But now we have two terms, and we can look at them and say, well, what is the probability of W? Well, in our training phase, we fix the W at the end because we learn the model, we find the optimal W. So in our training phase, we deal with the W, we deal with the training input, we deal with the training targets, but we don't have the test point yet. The test point comes later. So our probability for W should not depend on our test point. So we can throw that out. And here, we have the probability of the target. Well, this does not depend on our training data because we already fixed the W. So this dependency here is in fact not really depending on the training data, the training targets. It's only on the W which we have fixed and the new input point, X. So we come up with this, and that is in fact the way of calculating the predictive distribution. So it looks, when you just see, oh, this is the formula for the predictive distribution, you can try to reverse engineer this and figuring out how people came there, using A, the rules of probability, and B, what you know about this process. You know about testing and training, and you know that the only thing which is moved from training to testing is the W. So we can do this and calculate the predictive distribution. And this is again an experiment here. We take one data point here and we calculate the predictive distribution. And you will see that here are plotted 1 sigma variance between the mean, and so we can see how sure we are about the distribution of the data points here. So when we draw one data point here, you can see that this collapses. Because we have a data point, we become more certain that the data must be there. So when I predict there, I can be quite certain that the prediction should always be also be close there. If I want to predict something here, well, I haven't seen data, so I can't really say very much. Now, if we take a second data point, then our confidence also increases here, and it also increases in between. But here we don't know so well, so these are still uncertain areas. And if we go further, you see that whenever we get a data point, the predictive distribution in that region becomes smaller. And if you have enough data points, then you're basically left with some uncertainty. And the uncertainty will not go away, because this uncertainty is coming from the noise. And we have assumed noise in our process here, so we will not be able to reduce our uncertainty below the level of the noise. And you can also do the same what we did with the W's. We can draw samples. And so you see, if you have one data point, if you draw samples from this distribution, we will get things which are close to this data point, but in other areas you will get very strange behaviors, because you don't know very much. You get more data points, your samples from the posterior distribution increase, become closer to the data point. And if you have many data points, you will still get somehow different samples, but they are all close to each other now. Okay, I think that's where we should stop. So classification. Simplest examples, we have two different classes of data points, and we are trying to find a way to distinguish between these two. So the simplest is here that, let's say, we have a linear separation of these data points. We try to find a good separation between these data points here. Now, we can go and use a linear model, but we have one problem which is different from regression here. In regression, we were looking for instance, for real numbers. In classification, we are not really looking for real numbers, because there are infinitely many real numbers on the real line, even between 0 and 1, but we only want two classes. So we have to do something extra if we want to use a linear model. And the extra is that we need to apply some function which we compose with the regression model in order to get an output which is, for instance, 1 or minus 1 or 1 and 0. So we get two classes back. And though this is called a generalized linear model, we still have a linear model, but we wrap another function around it. And that's usually called an activation function. And here you have a simple example. It's just the sine function, which is +1 or -1. There's also a name for the inverse operation. It's called the link function. So we are dealing now with a generalized linear model. And well, we could go all through applying our regression results to that. And we would get some quite good result if we have this setup here. But if we use the same approach as in the regression and then just wrap an activation function around it, and we have some outliers here, then we have the same problem which we have with regression. These outliers, especially when you take the squared error as a measurement of error, these outliers will drive the partition between these two classes towards these outliers. The squared error will make this impact very high. So you will get this magenta line here as the classifier between red and blue, and of course that is not a good classifier. So we have to do something more clever. The same happens if you have three classes and you have them in this form here, then you will not be able to really find the third class, while a different method, which we will see later, called logistic regression. It is classification, but it's called logistic regression, just to make it hard for you. So that will do much better. Okay, I'll skip this here. There's some history in these slides about the perceptron algorithm, which was one of the very early algorithms which surprisingly converged to do classification. And I just want to mention there are different types of approaches. You can, for instance, just try to find a discriminant function. So you're not really dealing with probabilities and probability distributions. You just find a function, and if you apply it to the data, then it gives you the right class. So you're not modeling probabilities. You can use a discriminative model, where you try to model the probability of the class given some inputs. And that corresponds to what we have done in the regression with the maximum likelihood. Or you go to a generative model, and here, this is the Bayesian type approach, where we really try to model all the class conditional probabilities. And if we include a prior, then we can also work with the joint probabilities. Of course, if you go in this direction from top to bottom, you will see that you have to do more and more work, because you have to estimate the probabilities for a generative model here. So one generative approach is that, well, let's assume we have some probability that if it's class 1, then, if the probability of the data, if it is class 1, and then we add some prior to it. And then we normalize over this. So this is again Bayes here. So we get the probability of the class given the input. And now we can mathematically, just mathematically reformulate that by introducing some new definitions here. If we call this A of x just the logarithm of the quotient of the joint probabilities here, then we can write this here in the form of 1 over the 1 plus the exponent of minus A of x. And this 1 over the 1 plus the exponent of minus A of x is also called a sigmoid function. So it has this shape here. It's starting at 0. It crosses over the y-axis at 0.5, and then it saturates at 1. And so you can think of this as a better mean of trying to find a decision boundary between our two classes. Because in the least square case, we saw that these outliers are really influencing our solution very much. Here you can see this function saturates, so you can imagine that something which is very far away here doesn't really influence the solution anymore. What is really interesting is this middle part here in the sigmoid function, where we go from one to the other. And if you have multiple classes, more than 2 classes, you can also write it in this form, where you now have the exponent of this activation function here, and this activation is the joint probability of x and the class. So this is also called a softmax function, because if you analyze this more carefully, then you will see that in case one of these a's here is much larger than the others, then what will happen? Well, let's assume this k here is the k which has a much higher value than the others. Then this will be close to 1. That will be a very large number. This will also be a very large number, but because all the other a's are very small, it will have the same, almost the same magnitude as this, so we'll get a probability of close to 1 here. While for all the other classes for which this is not AK, that's AJ here, it will be small, but AK is still here the biggest influence, so we'll have a small number divided by a big number, so we'll get some small probability for the other classes. And we can do that, for instance, we can assume that our 3 classes are Gaussian distributed, and then if we apply the logarithm here, it will take down the exponent, and so we have a quadratic term in the exponent, which is now this a here. And what it will result in is that the decision boundaries between our three classes here will now have this shape here. The linear decision boundary here comes because this Gaussian distribution and this Gaussian distribution have the same covariance. Because they have the same covariance, only the linear part is different. While this one here has a different covariance to the others, so in this case, the quadratic part of the exponent will be taken the logarithm of it, and what we get is this quadratic boundary. So we have, for the Gaussian case, we only have two possible boundaries between our classes. It's linear or it's quadratic. Now that is already much better, but if you start to calculate the number of parameters you have to find, then we have to take into account that, for instance, we have to work with a Gaussian. And for a Gaussian, we have the mean and we have the covariance. And so, for instance, for two classes, and we have two means. And if we assume that everything is living in a m-dimensional feature space, then we have two means, 2m. And then for the shared covariance, we have a quadratic term here. So we have a quadratic number of parameters to estimate. And that, for larger problems, can become difficult. So another approach is logistic regression. And again, this is not regression, this is classification. So here, we code the membership as a number between 0 and 1. And then we have a likelihood function, which is just the product of each of these variables, which can be 0 and 1. And this is just a very fancy way of writing this yn. When t is 0, then this is 1, and we have 1 minus this, because this is the exponent is 1. And when tn is 1, then it's y. So it's just, if the class is the first class, then we have the probability y. If it's the second class, the probability is 1 minus y. So, but this is easier mathematically, so we code it in this a little bit a mouthful way of coding the fact that you have 1 minus the probability. Sorry, you have y or 1 minus y as a probability. Okay, and then we can come up with an error function, which is now the negative logarithm of the probability of the targets given our w's. And we get this here, which is a sum, because we have a discrete number of classes, and it's also only has two terms, because we have two possibilities. And this is called the cross entropy. So the error function is the cross entropy, and we can calculate the gradient of this error function. And using that, the sigmoid has a very nice gradient. So the sigmoid function, if you take the gradient, is just sigma times 1 minus sigma. And that is probably one of the reasons why it's often used. And then we come up with the gradient of the error function is just a sum over all these different possibilities. And here we have the real target and the output of our model, the difference between them multiplied with the feature feature phi here. So this has fewer number of parameters, and so for more complex problems, this is easier to estimate the parameters for this model than for the full generative model. Okay, I mentioned in the previous hour that features are often, if you get the features right, you already have 50% or more of your solution. So I just want to make this point again here and show you some graphical representation. Features means we take the input data and we transform them in some nonlinear way to get a different representation. A linear transformation doesn't really help us very much, at least as long as we are using linear methods, because a linear transformation will just let you be in the same linear space. So you need a nonlinear transformation. So if, for instance, we have these two classes here, we have the blue ones and we have the red ones, and you want to come up with a classifier, then, well, you could start and say, well, let's try to find circles which are able to classify that, but then we would have to calculate distances from circles and all this complicated stuff. But we could also say, well, let's take this point and let's take this point, and every data point now will be transformed into the distance from these two points. And then you get this representation here. Here you can see that for the distance from the red data point, that is the coordinate in this direction here, and the distance from this blue is in this direction. So you have a cloud of blue points here, and you have very far away another cloud of blue points, and the same way the red points are in the middle. And now, just doing this nonlinear transformation, it's easy to find a linear function which just separates these two clouds of data. So now you can use a linear method and you're done. So I want to stress this. If you can find a good feature representation, it makes your life much, much easier. And you should think about that, or you should use some method which allows you to try out different feature representations. And we will, I don't know if we have time enough today, but kernels, just to give you a hint, kernels are one way of looking into very high-dimensional feature spaces, even infinite-dimensional feature spaces. Okay, that is just what I said again. Things which are not linearly separable become linearly separable if you find a good transformation. Okay, so far we have all the time talked about features, and we had to choose the features and put them somewhere in the input space. But there's one problem. If our input space is very high-dimensional and we want a decent number of features, then we have to put a lot of features in this space, because we need to decide about the features before we even see the data. It would be better to have some machine learning approach where the features are, so to speak, moved to the regions in the input space where they make sense. So we don't throw so many resources into areas where we don't have data. And you can think of neural networks as one way of doing that. It's not the way it was probably invented, but it's one way of thinking about it. And you will hear more about neural networks when you go to the lecture about deep learning. So I just want to give you some basic concepts here. Who has heard about neural networks yet? I heard already, I mean. Most of you, that's good. So then we can go fast. So this is a neural network with one input layer. It has a hidden layer and it has an output layer. And what happens is that we sum the inputs with some weights, which we can think of on the edges. And then we get a result here. And then we apply a nonlinear function to the output here and create to the activation here and create another output, which then is fed into the next layer. So if you only look at this part here, and if you assume that the outputs don't have any nonlinear function, then this is a linear learning machine. But if you look at the formulas, you can think of the first part here as adaptable features or as adaptable basis functions. And just to show you some of them, this is the first layer of the network with a sigmoid activation function. So for the different choices of W, I get different functions here, because you can change the scale of the inputs here, and that means you move the sigmoid functions in the space. And you can also change how the relation between these inputs is. So you get these rotated versions. For instance here, if you have some of the inputs to 0, then you get a rotated version of the sigmoid. Here you get a shifted version because I have taken one of the inputs very high, so it's basically just almost 1 everywhere apart from this small part here. And so you can approximate functions with a neural network. Just a few examples here. If we have a quadratic function and we take as input this basis function, then we can combine them in a way which is quite close to the quadratic. And the same with the sine. Also, the input functions are looking not really like a sine function, but doing a clever combination, you get almost the same result. And even with functions which have non-smooth parts, like for instance the absolute function here, even taking this as input functions, you can get a good combination which represents them quite closely. Same with the Heaviside function, Heaviside function. And you can apply it to a two-class classification, even with overlapping classes. So for the optimal decision boundary here is the red one. Yeah. So more about this. I just want to mention here, for a long time people realized that neural networks are great because they have all this flexibility. But the biggest problem was, well, how do you find the best parameter settings? And that took quite some time to figure out, but finally people figured it out. And that's the backpropagation formula. So you basically calculate the gradient of the error of this neural network by first taking the error of the outputs, and then you go backwards by combining the outputs with the weights on these edges, and then summing it almost in the same fashion as you sum it when you go forward. But if you want the gradient of the error function with respect to W, you need to multiply it then with the derivative of the activation function at the activation value at the input. But that can be done, and so for some of the activation functions, you can really find very, very simple formulas just using some properties like that the hyperbolic tangents has a nice derivative here. So for this case, if you use the hyperbolic tangents, the derivative of your error function is just the error times the input. Okay, if you have the gradient, then, well, you can run an iterative process. You start somewhere, you calculate the gradient, you change your point to a more optimal point, and then you calculate the gradient again until you converge. Well, for most of the neural networks, there is not one point to converge to, but there are many local minima. So there are some subtleties involved, but I won't go there. I just want to add that, of course, the model complexity matters again. So you have to be aware of overfitting. If you take too many nodes as the hidden layer, then you will easily get something which really matches every point you want to, what you have in your training data. So you have to be careful not to overfit and take a smaller number of hidden layers. Or the other possibility is you start early, as you stop early when you do the learning process. You could, for instance, go on with training and training, and you fit better and better to your training data. But just to stop early and say, okay, it's enough. If I do more training now, I will overfit. That will result in some validation error, which is optimal here. Again, more details you will see in the lecture in next week, I think it is. Yeah, on the last day, so next Wednesday. Right. Okay. Now we are getting a little bit more, even more cursory than until now, but it's worth to mention kernel methods. And the idea here is that in the models we have looked at and so far, we always assumed there is a training phase where we estimate some parameters, and then if we have the parameter, the W, if it's fixed, then we apply that model to predict new data. But you're basically throwing away all the training data after that. You fix your W, and then you say, okay, forget about the training data. The W is all I really need now. So why not use the training data directly for prediction? I mean, we have training data, so we know that in the vicinity of a training point, things should somehow behave similar, or we believe that. We assume it's not a fractal system where things completely jump to something different. And one way of making this really more formal is kernels, where we can write the minimizing function in the following form. We have a loss function that measures our error. We have some penalty, which is quadratic in some f. And so we have the minimum. We are looking for the minimum of the penalized loss. And we assume that, and we find out that this has the form that there are some alphas multiplied with a kernel. Now, what is a kernel? A kernel is a function. I take two data points and I get back a number. And in fact, mathematically, it's the result of some inner product in some space which is derived from these data points. And in order to work, it has to be a kernel, so it needs to be positive semi-definite in the pairs of data points, in all possible pairs of data points. But the good thing is that this is now a kind of similarity measure. So we have something we can really reason about. And so I already said there is some space into which our inputs are mapped. And in that space, there is an inner product between these features. But the good thing is we don't really have to calculate this inner product. I cannot show it now to you, but I hope you believe me that if you take the norm between two vectors and you take the exponent of it, you have an infinite dimensional feature space. Now, taking the norm of a difference between two vectors, that just gives you a number, and exponentiating that is a very simple operation. Calculating a mapping into an infinite dimensional feature space is impossible on a computer because you don't have infinite dimensions. And then calculating the inner product between this impossible infinite dimensional feature spaces is also impossible. But we don't have to do all of that, because all we need is a function which somehow can be represented as an infinite, possibly infinite inner product in an infinite dimensional space. But we don't use that for calculating a kernel. We just, for instance, take the exponent of the norm of the difference, or the squared norm of the difference of our vectors. So that is all we need. And then we can solve our regression problem, for instance, by using this kernel. Now this kernel here is an inner product using this kernel function between all pairs of training data. And then we have a vector k here. This vector k is the inner product between all the the training data and a new data point for which we want to make a prediction. So we can just plug in these numbers. We need to invert this matrix here. Oops. And we apply it to our training target. And that for a given x, for a given new test point x, will give us the output of the model. Now there is something hidden here which, if you look closer at this, we now have a dimension here, which is the dimension of the number of data points we have in our training set. So if you have 1 million data points in your training set, then you will have 1,000,000 by 1,000,000 matrix. And not only that, you also have to invert that. And that is, I would claim, even with our computers now, with best computers, not possible. So instead of the number of parameters which we had in our original approach where we had a W vector, and we chose the number of features, and we could make it small or big as we wanted, now we have to deal with all the data points, the number of all the data points in our training set. So we have to pay something for this, but we also gain something from it. And before we go there, just to give you some examples, if you have polynomial basis functions, again, this is not a clever choice for most cases. So if we keep one input vector here and we vary the other vector, then we will get this kind of kernel value. If we do it with Gaussian basis function, so we map one here and then we vary the other input here, so we get this. And so you can clearly see here, this is a nice similarity measure. If our two inputs are the same here, then we get the biggest value for our kernel function. If they are very different, then we get a small similarity. Same with logistic function. I already mentioned that it's easy to create features and new features, and here I want to illustrate that. If we, for instance, decide that our kernel function is just the inner product between x and z squared, I mean, the inner product is a number, we can just square it. It's an easy operation. Now we can ask the question, what kind of features does this operation really represent? So we take, for instance, a two-dimensional input vector. So our inner product is this here. And if we square this, we get these three terms here. But now if we look closer, we can write this as an inner product. It's the inner product with x1 squared and z squared, x2 squared, z squared. And then we have a third term here, which is root of 2, which is a product of x1 and x2. So we have a new feature here. This feature is the product of x1 and x2. Now, as I told you, you don't have to do this explicitly. You just get it for free by taking the inner product and squaring. Now, squaring a number is a very, very cheap operation, but behind the scenes, you already work in a feature space of 3 dimension, which has this interesting nonlinear part here. Here's some theory. I already mentioned the positive semi-definiteness for the Gram matrix. And I think I leave it here. Just to give you an idea, there are rules. So somebody sat down and said, okay, if I have this and this and this, and I combine it in this and this way, is this again a kernel? So you have many rules how to create new kernels from old kernels, or from extra things like functions, composed with a function q, exponential of some kernel, sums, products, and so on. And I showed you already some example here with m equal 2. So you get all terms of degree m. If you add some constant here, you get all terms up to degree m. So you get all, if m is equal to 3, you get a constant linear terms, quadratic terms, and third order terms. And this is the Gaussian kernel I talked about. You take the difference between 2 vectors and you square it and exponentiate it. So with kernels, we only need an appropriate similarity measure. But if you have to solve a machine learning problem, you might have an inkling what the similarity in your input space really means, because you might have some domain knowledge. So that helps you on the practical side to choose a nice kernel, because the kernel gives you an intuition. It's a similarity measure. What is more, you can define kernels over things for which we until now didn't have an idea how to deal with. So for instance, if we have sets, then we can create the power set. That's the set of all subsets of a set. And then we can, for instance, define the similarity of 2 sets by just taking the intersection between the 2 sets. So if A1 and A2 are the same, then the intersection is the whole set. If they are completely disjoint, then the intersection is the empty set, and so the cardinality will be 0. So again, we have the similarity measure. And then it can be shown that if we construct a kernel in such a way that we take 2 to the power of the number of the elements in the intersection between these 2 sets, that we have a valid kernel function here. So we have a valid similarity, which we can now apply all algorithms. So we can work with sets, and that means we can work now with strings, documents, a lot of things which up to now, we didn't have an idea how to do it. Okay, I already mentioned, so we have an n times n matrix, so we have to do more work, because depending on the number of data points, the matrices can become very large. We can construct new valid kernels. That's a good thing. And we have some intuition what it really is to be a kernel. We have some idea about this. And we can apply that now to much broader set of things. For instance, we can work on graphs, on sets, on strings, on text documents, and so on. Okay, let me see. We can try and solve these huge matrices, but it turns out not all of the data points are really equal. So input spaces are not really democracies. Some of the data points are more interesting to us than others. So think of, for instance, for a classification problem, the decision boundary between the two classes is defined by the points which are closest to this decision boundary. The points which are out here, they are not really interesting for that. So the points which really matter are the points which are closest to this region which is between the two classes. And we can make that a little bit more formal by using what's called a maximum margin classifier. So we are looking for the classifier which gives us the biggest margin between the two classes here. So we take the closest point of two classes and then we put that in the middle. And that can be mathematically represented as an optimization problem in which we will figure out that some of the data points here, they get values alpha, which are 0, so they don't contribute to the solution. So we don't need to think about them. And others will contribute, though they are lying close to the decision boundary between these two classes. And this allows us now to reduce the number of data points which we have to take into account. We still have to solve the problem for all the data points, but for many of them, we find that the alphas here are contributing nothing because the alphas are 0. And then we can reformulate our solution just in terms of these data points which are close. And that's why they are called the support vectors. So that's a support vector machine. And we can even deal with cases where the classes are overlapping. So even in the case when there are data points, some of the data points are on the wrong side, we can still work with those. So what we find is, for instance, for this case here, the blue data and the red data are two classes which are overlapping. We still find a decision boundary which goes around this here, and we also find some here. There's another approach, which is a Bayesian approach to this problem. I cannot really go into all the details here. So I will just mention that we are assuming here that each of the components of the W has its own precision, its own variance. And if we do that, we can set up an optimization problem which has some disadvantages. It's non-convex. It takes much, much longer than to train a support vector machine. But if we have a solution, then it's a Bayesian method. So it can take care of complexity and noise. And the number of the relevance vectors, the number of vectors in which our solution is defined is much smaller than for the support vector machine. And that means that prediction then is much faster. So we have to put some more effort into it up front. But then we get a faster solution. So here's an example. The relevance vectors, they are now no longer close to the decision boundary. But if you look at the number of the relevance vectors, there's a much smaller number of relevance vectors describing this solution here than for the support vector machine. Okay, so, and final slide for this. Because it's a Bayesian approach, we do not only get the decision boundary here, we get a real distribution. So you can, for instance, see that in some areas, the distribution of the blue points is much more concentrated than it's in other parts here. Again, it's a Bayesian approach. We do not just get a number or a solution for a decision boundary. We get the whole density over the problem. Okay, we will not go to mixture models. I will jump forward, and you will probably appreciate that we don't do that. We also will not do sampling, although I recommend you, if you have never looked deeper into sampling, it's quite interesting, you should do. It will not be in any of the lectures in, we have some MCMC stuff. No? Yeah, okay, great, good. Okay, I have a few slides here just to tell you a little bit about how to do machine learning. This is not how you must do it, but this is a little bit of advice how you could do it, and it could save you quite some time. So if you compare the machine learning area to other areas, especially if you compare it to medicine, then you will realize that in order to get a medical paper published, if you do experiments, you have to be very, very careful. You have to do a lot of experiments, you have to document that, and so on. In machine learning, we are still, but you should be able years later to reproduce the result and compare it with something new you might have found. So that's something we really should strive for, reproducibility of results. And the best, of course, is if you publish something, then you also make available your code and the way you set up the experiment. Because very often, even if you have the code, you're sometimes missing parameters which were used. So to have a complete reproducibility of your experiment, that is the goal. And that will save other people a lot of time, but it will also save you a lot of time because you might want to compare some newer result with what you have done a month ago or so. So that is the intuition or the intention here. Results need to be reproducible and you need to publish them. So no-brainer, use version control. If you haven't done yet, I would probably recommend Git, and it's a little bit more complicated than others. But the great thing about Git is that you can do local commits. So that means you don't need to push into some common repository where other people get every small increment of your code. You can push it into your own local copy of, your local clone of the repository. And that way you can experiment with your code and you can always go back to some previous experiment. So please get used to this and use it often. Separate the code from data. I think I had to deal a couple of times with repositories where, for instance, somebody studying Go had put in 20 gigabytes of Go games into the repository. And of course, nobody ever touched this data again. They were just sitting in the repository. And everybody who wanted to clone the repository had to first clone 20 gigabytes of Go data. Although you might just want to look at one file, one algorithm or so. You were not even interested in the data. So separate data because data are not often changing. You have work data. That is a different thing. You have input data, not often changing. You have output data, which are generated and which might not change too often because you want to keep them because you have published. So make a distinction between them. Work data you can mostly throw away because if you have your code, if you have your input data, you should always be able to reproduce your work data. Separate code from data. Clearly, I already made these points here. And try to save stuff to disk, even results. It's happened quite often that you talk to somebody and can you please give me the results you did 2 weeks ago? Sorry, the code has changed. I've deleted the output. It's gone. So what did we do 2 weeks ago? I might sit down. It takes me an hour to reproduce that. but we already did it. So one way is, of course, to use just some naming scheme where you have days and some descriptive parameters, and you put some stuff there. But you can choose other ways of describing your experiments. Yeah, I think that's obvious. You need to have a full description of what the parameters have been, and possibly also have some way of describing what these parameters really mean. That's just good documentation. This is a word of advice here. Don't forget the random generator. We are doing machine learning, and we often have randomness in the way we set up our machine learning algorithms. Now, if you want to reproduce an experiment and you don't take care of the randomness in your random generator, you might just choose a different set of random variables. And then you will never be able to reproduce your experiment. So you need to make sure, first of all, you need to make sure that you set your random generator to a specific value, and you can do this by using some seeds. But you need to also think about in which part of your algorithm random numbers are used. Because if later on you execute this, let's say you have two parts where random numbers are used, you execute them in a different order, then of course you will get different random data. And again, your data will not be reproducible. Yeah, this is just, MATLAB, for instance, had this problem that they had different random generators for rand and rand-n. That means if you wanted uniform distributed random numbers, they used a different random number generator than rand-n. So there was, again, some dependency on, you have different types of random generators. And then be clever and set up experiments so that the computer does something while you sleep. That means also to have really an experiment set up in such a way that it can be automated. So you choose parameters through which you want to go. You set up some loops, and then you just let it run overnight, and the next morning you get your hopefully great results back. So make it in such a way that you can execute the experiment again. And one way I showed you was to, for instance, to use a Python notebook. It can be executed. You can execute a whole Python notebook, and that could be your experiment. You just run it. This is another thing. If you're working with longer running algorithms, try to save some state, because it is quite cumbersome to run something for, let's say, 10 minutes, and then it crashes. And you have 10 minutes left. You have 10 minutes lost. So if you have longer running algorithms, try to save intermediate results. So whenever something goes wrong in the later stages, you don't have to start from scratch. And that might involve very simple things like, for instance, you read some ASCII data, huge ASCII data, you save them as binary file. That already can help you very much. There are very, very efficient compressing algorithms. I don't know if you've heard of BLOSK, for instance. Very efficient, much faster than gzip. Not as good in compression, but very, very fast. So you can save stuff, big stuff to disk in short time. So put in checkpoints and make sure that you save intermediate results if it's for longer operations. And there are a few other things. Don't use global variables, write tests, and so on. Finally, I just want to mention, at the end of the slides, you find some journals, you find some conferences related to machine learning, and you find some nice books. This one is especially nice because it's online, so you can get it for free, and it's a good book. And there are some other machine learning books which have recently been published. Kevin Murphy has a lot of algorithms. This is more in connecting theory and algorithms. I've used some of the slides from the Bishop book, as you might have seen. And then there is a classic Tip Sharani book. And these two. Okay, there are, of course, more and more data sets available. These are just some of the available data sets. So if you're looking for some interesting data sets, go there. And that's it for today, almost, for the morning. Thank you.
So we have time for some questions. So, yeah, any questions?
All clear.
Everything was clear? Perfect. Can you try speaking from there? And if not, I'll take a microphone.
You mentioned in the very beginning about some links between game theory and machine learning that were recent. I wonder if you could just very quickly mention some papers or some areas that you were referring to.
Yeah, so the question is, I mentioned some relations between game theory and machine learning. There is the concept of prediction markets, which you might have heard about, that, for instance, in the US election, people bet on different candidates to become the president. And on the surface, it looked for a long time that there is no relation to machine learning, but people are now exploring that the way prediction markets work are related to machine learning problems. And if you establish this kind of link between different fields, then of course people go over this bridge and now they look at, on one side, what do we have? Can we use it on the other side? So that's, for instance, one example.